Very much everyone for joining us. Today we are talking about distributed Java databases under the hood, main component and interactions with them. The speaker today is Valentine Klichenko. He is the GridGain Director of Product Management. He's also a passionate open source Apache Ignite community member and a PMC member. He dedicated his time to public speaking, contributing code, and providing technical help throughout the dev and the user mailing list. This event is organized by RickWorks on behalf of the London Java Community Group. And if you want to talk about yourself, Valentine, for a second, it would be appreciated. Thank you very much.
Yeah, well, I dedicate my life to this to a certain extent, I guess. Yeah, thanks for the introduction. Hello, everyone. Yeah, my name is Valentin. I'm a product manager, part of the product management team at GridGain Systems. I used to be a developer as well, and worked with our customers and all. So I'm at GridGain for the last like 10 years or something, and I've been working with distributed systems for all those years. And we also, around 5 years ago, we've started the Apache Ignite project, which kind of was the donation from GridGain. So I'm in this field for quite a while. So what I wanted to do today is talk about how distributed databases work under the hood, how they work internally. The thing is that what I've noticed and continue to notice is that a lot of developers and architects who start using distributed systems, they kind of treat them as a black box, because there are a lot of just basic marketing promises that you will take a distributed database and it will provide you scalability, it will provide performance, and everything will be 100x faster or whatnot. But in reality, of course, that's not how it works. Distributed systems come with a lot of trade-offs. Scalability itself comes with a price, and it's important to understand how they actually work, how they function, and what are the main internal components that affect the scalability and performance in order to get kind of the most of these kind of systems. So I wanted to share a little bit of that experience, and what I will do today is basically build a database from scratch, kind of. I will create an architecture. I'll have like an architectural diagram, which I will create step by step, adding more and more components along the way. And also we'll take a look at the code as well. So I had this very basic implementation, and I will also kind of once I add something within the architecture, I will also show how it looks in code, so that you get a little bit more understanding of how it works. It will be, of course, very basic implementation, not production ready by any means or anything, but it's actually will be functional, and I will talk about what it will be able to do in more detail. All right. Before we go there, so we have a raffle today. So you can win one of these 3 books. So I will leave the slide for half a minute or so. So basically what you need to do is grab this link, and there will be a very short survey. And if you fill it in, you will have a chance to win a book. And at the end of the presentation, we'll announce 3 winners. I think Ksenia is online. So Ksenia, if you want to add something, go ahead.
I just put the link in the chat, so you can go on with the presentation. And at the end, we'll do raffle by using our magic button, random winner. So everyone who will fill out that survey will have a chance to get one of the books of your choice, and that could be paper one, and that could be Kindle one. We'll decide that later when I'll contact you.
Sounds good. Thank you. All right. I'll bring the slide backup in there as well, so that if you didn't have a chance to get the link, you will have a chance. So let's move on. Let's start building our database. So as I said, of course, like the first and foremost, we need to define the requirements for the database, just to make sure we understand what it can do and what we want to implement. So there will be several requirements. As I said, it will be a very basic implementation, nothing fancy. The first requirement is in memory data storage. Memory databases are actually quite important these days. So I'm kind of doing this for simplicity, not to worry about, persistent disk-based storages and all the complications that come with that. But it's also quite an important part of distributed databases field in general. In memory databases are becoming more and more popular and more prominent in the industry. So I will be working just within memory data storage. The second requirement is the API. The API, again, it will be very basic. It will be a key value API with just two methods, put and get. Again, of course, in a real database, you will have much more APIs. Like if you look at the Apache Ignite, for example, it does have a key value API with much more than two methods, of course, but it also has SQL, it has computational capabilities and whatnot. We'll stick to very simple key value APIs with just two methods here. The third requirement is scalability. Scalability, of course, is essentially what we are looking for when we want to use a distributed system or a built distributed system. This is basically why we're going with a distributed system in the first place. It must provide scalability. By scalability, what I mean here is just basic ability to have multiple computers that would join together, kind of form a single cluster, a single entity that can be treated by the applications as a single entity, as a single database, right? Meaning that the application accesses the database through public methods, through public APIs. In our case, that's method put and method get. And it's basically abstracted from the fact that there are multiple computers. It doesn't really have to know how many servers there are, and whether topology changes or not, these kind of things. So again, this is just a basic ability to have multiple computers that form a single database that is visible to the application as a single database. If we go into detail, scalability has kind of two aspects, at least most important aspects that I would like to cover. And they basically create those other two requirements that I have here. So the first aspect of scalability is what I call computational scalability. What it means is that you want different requests from the application somehow be routed to different servers in your cluster, in your distributed database, right? So if you have, let's say, an application that creates 1,000 operations per second, and you have two servers in your database, you want approximately 500 of those requests to be processed on each server. And if the load increases over time, you want to be able to just add more servers so that the system can handle this overall load. And the second aspect is data scalability, which is a little bit more straightforward. It just means that I want to be able to store more data by adding more computers in the system. So let's say if I store the data in memory, the memory is quite limited, of course. And if I have, I don't know, like 100 gigabytes of RAM per server, I want to be able to store 300 gigabytes of data if I have 3 servers, right? And if again, if data set grows over time, which which happens, I want to just add more servers into the system, increasing the overall capacity of the database. And both of those things must happen automatically by the system itself. So again, the application only knows about the public methods. It only invokes those public methods, method put and method get, and system then needs to have a mechanism, like an internal mechanism, that would route those requests automatically to different servers and do that consistently, of course, and also distribute the data automatically as well. All right, so these are the requirements. Again, these are very basic requirements. Actual real database will, of course, have much more, but we're sticking with simple things. So let's start building the actual architecture. So as I said, I will have like an architectural diagram at the end, and we'll be building it, step by step along the way. So if we look at our first requirements, the first requirements was the in-memory data storage, and the second requirement was the put and get API. So let's actually start there. So first of all, we need some kind of a storage, right? So that would be our first component, the actual storage that will store the data on a server instance. So this blue box, big blue box, is essentially a server-side process. It is the process that will run on every server that we want to be a part of our database. And the first component within that process will be the storage. In our case, since it's just in the memory storage and it's also only has key value API, we can just use simple concurrent hash map if we're doing that in Java. Again, of course, the underlying data structure might be different, and it will typically be different, but for our requirements, that's enough. So once we have the storage, we need a mechanism for a client to access this storage across the network, right? So we will have a remote client that will access that will connect to the server-side process and will get the access to the storage, and therefore we need some kind of a communication layer. This communication layer will be responsible for all the all the networking stuff, of course, like creating sockets, creating connections, accepting connections, maintaining connections, and all that. And we're also responsible for essentially serialization protocol between the server and the client. And on the client side, we'll, of course, need the same communication layer so that they can communicate with each other. Again, it will be responsible for networking, and it will also understand the same communication protocol. So this way, we just make sure that they can talk to each other and understand each other. And it will also have the public API with those methods that we want to have there. The application itself will kind of embed this client instance, and I will show that in the code. And this client instance will therefore provide those public APIs to the application. And the application can just create an instance of a client within itself, within the same JVM, and just invoke public methods. And the API will go through the communication layer to the server node. Server node will access the storage and either update the data or read the data. So let's see how it looks in the code. So again, as I said, I have this project which is on GitHub, and at the end we'll share all the links to the code, and you will be able to play with it and do any modifications if you want or whatnot. I will just briefly go through the project, and again I will go add more things step by step, but basically I will just show you how it works. So, and it will reflect exactly what I have on the architectural diagram. So as I said, we have the server process, and the first component within that server process is the storage. The storage is very straightforward. As I said, we can just use concurrent hash map, so it because of our requirements. And the storage will have put and get methods. These are not public methods yet. These are just kind of internal private API, which can be used by other components. In particular, it will be used by the communication layer when requests are coming in. But basically, very straightforward. We just have a concurrent hash map as an underlying data structure, and we have those methods that simply delegate to this concurrent hash map. Then we have a communication layer. Again, it's pretty straightforward. It has a couple of methods. It has a start method, which just creates a server socket and to start listening for requests. Is also picks one of the available ports so that I can start multiple processes on a single machine. And the listen method just, creates, accepts connections and creates processing threads. I'm using like very basic vanilla Java API for simplicity. It's basically kind of a thread per connection model, which of course will not be used in any real database. I'm doing all this. I'm doing many things just for simplicity's sake here. So what happens here is, again, as I said, it has to implement certain protocol, kind of communication protocol between the client and the server. The way it's implemented there is, the way it's implemented here is through this request interface, which is basically kind of the entry point for the communication protocol. It implements any request that happens within the system. And the request interface is very simple. It just has a handle method where we provide the storage, because any operation that actually happens within the system will be applied to the storage. And the communication layer for any request coming in, so it will deserialize it here from the socket stream. And for any request that it receives, it will invoke the handle method with the provided storage. And this kind of creates this link between the storage and the communication layer. And whatever is returned from the handle method is written back to the output stream. And finally, there is this execute method, which is for now will be used only on client side, because it's kind of other way around. It sends a request to a server node. So it gets a request and an address, and it just creates a connection and sends that request to that address. So to kind of combine all that, we have the server class, which implements our server process. It has communication, it has the storage, again, just as shown on our diagram. It starts the communication, initiates the listening, and we have a main method that starts it. So, and the client looks like this. So we have communication here. We don't have storage, of course, because the storage is only on the server side. It also has a start method, which is for now empty. We'll use that going forward. Currently, it doesn't have any life cycle because we don't have to start communication here. We don't have to listen on requests, of course, right? We only use communication in the client to send requests to the server nodes. It doesn't listen to any incoming connection. So we don't use those start and listen methods here. And these put and get methods here are our public methods. So these are the methods that will be used by the application. And what happens within those methods is basically we are invoking the execute method on the communication layer, providing a certain implementation of a request and an address of the server node. So for now, the address is hard-coded, which of course will change going forward. For now, it's just hard-coded to the localhost and the default port number for the server node. And if we look at the implementation of a request, just as an example, this is the put request, for example. So it has key and value, of course, which is sent across to the server node along with the request itself. And when the request is received by the server, it will invoke the handle method and will just delegate to the storage, and the storage will be updated this way. So this is kind of, again, this is basically the whole process. So the client sends a request here. It is being received by the server, and the server invokes the handle method, updating the storage here. And of course, the same happens for the get request. It's just it only has the key, because we're reading by the key, and the storage, we're using the get method on the storage and returning the value back. So, and if you look at the main method, it basically kind of demonstrates how the application will look like, right? So again, the application will embed a client instance. So we'll create a new client and we'll start it. And then once it is started, we can use all those public API methods that we have. We have only two. So for example, we can do several puts and we can do several reads. So let's try running something. So I'll start a single server node. So I'll just start a server here. Okay. Yeah, so the server is started, and the client. So I expect that the client will connect to the servers to the server that I've just started. We'll update the data. We'll write those 10 entries, and then we'll read them back. So if we look at the client log, everything was correct. So we were able to read data back and get the correct values. And if we look at the server side, it was actually was able to process all those requests. So basically, we've built kind of a single node database, which of course is not that exciting. It's not a distributed system yet. We want to have multiple servers, multiple server processes participating in data storage and processing the data. So let's move on to scalability, which is again, which is what we actually want from a distributed system. So as I said, by scalability for now, I just imply that we have multiple servers, multiple instances of the server process that form a single database. So let's add one more. This is the exact same server process. It has all the same components and runs in the exact same way. And the client can connect to both of them. So, of course, it's not a cluster yet because they are not aware of each other. We just started two separate processes. They don't know about each other. They don't know that they are part of a single database. And the client as well. The client also doesn't know about this. It doesn't know that there are two nodes. It doesn't know that it connect to either of them. Like technically, yeah, it can send requests to different nodes, but there is no information maintained anywhere, and there's no way for the client instance to automatically send a request somewhere. So we need some kind of especially kind of meta storage for this kind of data, right? That would maintain the information about the cluster, maintain the information about the number of nodes that we have and all that. So the way it can be implemented, I mean, it actually varies. Different systems approach it differently. Like, you know, any mature database would typically have kind of an embedded out-of-the-box meta storage that would be responsible for that. Another typical way is to have this kind of storage externally. Like in the Java world, for example, we have Apache Zookeeper, which is a very typical tool for this kind of purposes. I, in my code, will actually use the database that is called etcd, which is kind of a very, you know, basic key value database used by Kubernetes, for example, among other things. So what happens is that I will add another component, which is called discovery, and this component will be responsible for exactly what I've just described. It will be responsible for maintaining all the information about the cluster, about how many nodes we have, where those nodes are located, meaning like what are the IP addresses of those nodes, port numbers, and all that. Usually you will also have some additional information, some additional attributes, maybe some configurations, anything that has to be distributed across the cluster and be consistent across all the nodes. These kind of things are generally taken care of by this discovery component. So what will happen is that whenever a new node starts, it will first get the data from this etcd database, from this meta storage, which will essentially be the list of nodes that are currently in the cluster. It will also kind of subscribe to updates, so that, you know, if anything changes, it will get those updates. And then it will write its own information to the database, right? So when we start, imagine you have one node, and this one node already has written its own information into the database. So this etcd will have kind of one record for this node. When the second node joins, it will first get the information about the first node, and then also write the information about itself. And the first node will also get the information about the second node because it's subscribed to those updates, kind of listens to those updates. And this way, both nodes will always know that there are two nodes in the cluster, and they are part of the same cluster, and will also know where those nodes are located. So that kind of creates this awareness on the server side. But how about the client, right? The client also needs to know how many nodes we have in the cluster and where those nodes are located to be able to then route requests and distribute the data and whatnot. So for that, we'll actually add the same discovery component here as well to the client. And this discovery component will basically work in the same way. It will also connect to the same etcd database, to the same meta storage, and get the information from there. The only difference is that, of course, client doesn't have to write its own information. It will use this meta storage in kind of read-only mode, basically, without writing anything back. So let's see. Let's go back to the code. Let's see how it looks. So I'll switch to another branch here to get some more additions. All right. So the main addition here is, of course, the discovery component. That actually has quite a bit of boilerplate code because of the etcd API mainly. So I'll just show main parts here. So first of all, we have this topology map. So this topology map will maintain the information about topology. Again, about how many nodes we have and where those nodes are located. The UUID is kind of a unique ID for every node. So every node will have a unique ID, which will be randomly generated on startup. And this integer used as a value is actually the local port of that node. So this implementation assumes that everything is local. Of course, in the real system, again, you will have like an IP address here, of course, at the minimum, and potentially some other additional information as well. So this map, what's important is that this map will be maintained on every single node independently, but the goal is to make sure that this information is consistent across every node, right? So that's the whole purpose of the discovery component. That's what it tries to achieve. So the join method will be invoked on the startup, and every node will provide its own local ID and its own local port. It will connect to the etcd database, which I already have up and running, by the way, on my laptop. And then it will go through those three steps that I've described earlier. So it first will get all the information about the current nodes. So whatever is in topology right now will be acquired through this first step and will be written to the topology map. The second step is to create what is called so-called watch. So it's basically kind of a listener. Watch is a etcd terminology, but it's basically a listener for updates. So whenever something is written, something new is written, we will get a notification. And when we get a notification, we will also add this into this map as well, and also print out the new topology. And as a third step, we will register our local information into the etcd database by writing the local ID and the local port into the list. And we also have a get topology method, which can be used by other components to get the whole, the full list of nodes that we currently have. So that's the actual implementation of the discovery. So the way we add it into the server side is that we have the discovery component created here, and within the start method, we invoke join method on discovery, providing the port number, which is returned by the communication, right? So communication first starts, binds to certain port number, and this port number is then forwarded to the discovery so that it can be written to the meta storage. And the ID is just randomly generated for every node. And on the client side, we have the same thing. The only difference is that we don't need to provide ID or port number, because again, we don't write anything into the database for clients. They only read the data from there. So let's try running this, see what changes. So I will start a server again. And of course, this time I will start a couple of server nodes, because we want to have a distributed database. Okay, so it is started, and it actually shows the topology that has one node, which is expected. So let's start one more. So the second server shows that we have two servers, so everything works as expected. It got the information from the meta storage and also added its own information. And if we go back to the server number one, it also has detected this change, and it shows that we have two servers. So let's start the client. That would be our, the same application that I've had before. There are no changes. Does 10 writes, 10 reads. So we have discovery on the client side as well, and it was able to read the data from the meta storage and show us that we have two nodes. So we are good here, and the results are correct. However, if we look at the server side logs, we'll see that this first server still processes all the 10 updates and 10 reads, and the server number 2 is actually idle. Nothing happened here. This is, of course, this happens, of course, because we have this address here hard-coded, which brings us to our next requirement, which is automatic request routing. So we want different update requests and different read requests to go to different nodes, which doesn't happen right now. It always goes to this single node, which is based on just hard-coded IP address. And if we look at the diagram, the reason for that actually becomes quite obvious. We have discovery component, which maintains all this information, but it's not really used by anyone, right? Other components are not utilizing this information that we have, that discovery component can provide. So let's see how we can use this information. This information by itself, of course, doesn't show us how to route requests. It's just a list of nodes. So we need something else. We need some other additional mechanism that will decide to which node send a certain request, right? So for that, on the client side, we'll add another component which will be responsible for that. And the component will be called mapper. This mapper component will essentially provide us with a node, with information about the node, like address or anything else that we might need, based on the key that is being updated or that is being requested. So we have a key value operation, we get the key, and the API essentially will provide the key to the mapper. The mapper that then will go to the discovery, ask for the topology, which is essentially the list of nodes that we have in the cluster, then do some magic there based on the key that it got from the API and the topology that it got from discovery, and give the address of the node back to the API, and then the API will be able to go through the communication to a particular node rather than just going to a random node or to a hard-coded node, right? So the question is, what is that magic that happens within the mapper? So how would mapper decide which node to choose for a certain key? And of course, the requirement is that this decision must always be consistent, right? So if we invoke this node function on the mapper multiple times for the same topology, it always has to give us, and for the same key, it always has to give us the same result. And of course, kind of an obvious solution for this is hashing. If you work with any even hash table data structures or anything similar, you would probably think about this as a solution, because hashing is a very good way to get this kind of create this kind of consistent functions that would give us consistent results. So we'll start with a very simple hashing function where we will get the list of nodes from topology. We will then calculate the hash code of the key, just using standard Java method for now. We will also get the absolute value to kind of get rid of negative values, and then apply modulo function based on the number of nodes that we have. And that will give us basically give us the index in the list. And assuming that, again, as long as topology doesn't change, we'll always get the same index and we'll always get the same address for a certain key this way. So going back to the code, switching to a new one. So close this stuff. So let's see what happened, what changed here. So first of all, we have this mapper component here added, which basically implements what I've just shown. It has discovery, which is provided through a constructor, kind of injected into the mapper because we want to use the discovery component that we have already created. And the node method gets the topology from discovery, calculates the index like this, calculates the hash code, applies the modulo based on the topology size, and then gets the actual node information based on that index. On the client here, what happens is that we have mapper introduced here as well. It gets the discovery because it basically kind of depends on discovery here. And now in the put and get methods, we can use the mapper to get the address instead of hard coding it. So we first get the mapping for the key, and we get this node information, which is kind of a descriptor. It only has the ID and the address for now. But again, as I said, it can have a lot of other stuff as well, right? It can have additional attributes, any other meta information that you might be interested in. For now, it's just a local ID and address. And that's what we actually need in the client, because we need the address to know the address where to send the request. So this way we avoid this hard coding and we avoid sending a request to a single node. So let's see what happens. What happens now? So the server doesn't change. It still works in the same way it's used to work. So let's start those two nodes again. So we have the first node. Let's start the second one. All right, and let's start the client. All right, so again, on the client side, everything looks good. And if we look at the server side logs, we'll actually see that now first server only processed 5 update requests and 5 read requests for the same keys, which is, of course, kind of, which is basically guaranteed by this hashing mechanism, hashing algorithm. For the same key, we get the same result. Therefore, any operation for the same key will go to the same node. And the second server does the same, but for other 5 keys in the data set. So before we move forward, let me do one more test. So we have 2 nodes, right? But what if I want to add another node? Like a third one. As I said, we want to be able to do this to store more data and to process more requests. So we now have 3 nodes in the topology, and all the server nodes detected that. Now, if I run the client, I will run the client. The only change I will do, though, is I will remove the updates. I will run the same exact application, but will only do read operations, right? So yeah, we'll start a client, connect to the cluster, and read those 10 entries that are already in the database. I did not restart anything or remove the data, so it's still there. So I'm naturally expecting that I will get all the correct results from the database. Because remember, application must be abstracted by the fact that there are multiple nodes, and the application and the user of the database doesn't have to worry about the fact that I've just changed the topology. However, in the current implementation, that's not the case, because I've got multiple nulls here. I was able to read only 2 records out of 10. The reason for that is, of course, because once the topology changed, the mapping changed. Our hashing algorithm started giving different results. And for example, some of those requests came to this 3rd node, which of course doesn't have any data. All the data was saved on first 2 nodes. This 3rd node doesn't have any data, and therefore requests that are coming in here provide null values, which is incorrect, which is inconsistent data. Which essentially brings us to our final requirement, which is automatic data distribution. And the reason why I've done this test is that basically, if you think about this, we already achieved distribution to a certain extent, because if we send update requests to different nodes, the data is being saved on different nodes as well, and therefore it's kind of distributed. However, it only works as long as we don't change the topology. We don't add new nodes or remove nodes or whatnot, which is, of course, not acceptable. We need to also have a mechanism for redistributing the data across the cluster when this kind of events happen, when we add nodes or when we remove nodes from our cluster. So this is usually called data rebalancing, which is basically what I've just described. Rebalancing is the process of data redistribution, data reshuffling among the nodes based on the current topology. And the requirement is what we should want from the rebalancing process is for it to make sure that the data distribution is consistent with the request routing mapping, right? Because if you think about this, if we send a request to read a certain entry, for example, we want this entry to be stored on that node, right? Therefore, we want this rebalancing to essentially utilize the same mapping mechanism, the same hashing function in our case that is used for that. So we'll actually add this mapper component to the server side as well. So what will happen during rebalancing is the following. So whenever the topology changes, Discovery will detect that, right? Because it has all the mechanisms, it has its this watch enabled, so it will get the notification that a new node joined, for example. And once this happens, Discovery can notify the storage about that. So it will just trivial redirect of this notification from Discovery to the storage. The storage then, when it finds out that there was a topology change, it will be able to go through the data that the storage has, basically go through all the keys, and for every key, ask the mapper where this key should be stored. Based on the same mechanism, the mapper will go to the discovery for topology, do the hashing, and tell the storage back which node this particular key should be stored. And then the storage will decide if basically this key belongs to this local node, it will keep it. If not, it will send it to the node where it actually belongs. And this, of course, will happen through the communication layer. This red arrow here basically just shows the whole rebalancing process, kind of the data movement across the nodes through the communication layer. So the only problem with that, so it all works, and it will make sure that, you know, once the topology changes, the data is reshuffled and redistributed across the nodes based on the mapping that is also used for the request routing, so they will be consistent. So that's all good. The only problem with that is efficiency of the whole process. So as I said, the storage will have to essentially go through every key to verify whether this key is belongs to this node or not, which of course is not very efficient. We don't want rebalancing to be dependent on how many keys we have, or, you know, how much data we have, because we can have a lot of keys, of course, in the database. And if you think about this, now every time we add a new node, our database will have to iterate through the whole data set that we have, which might be a lot. And we, of course, we definitely want to avoid this. One of the ways to avoid this, which is basically just used in probably any key value database, not only key value database even, but in any distributed database, is partitioning. Partitioning is quite a, you know, simple technique, which basically just says, let's split our data that we have into groups, or as we call them, partitions. And the number of partitions will never change. It will not depend on how many nodes we have. It will not depend on how many keys we have, or it doesn't even depend on whether we have any data or not. This is the constant number of partitions that we have in the database. So for example, we're saying we have 10 partitions, and we start with 2 nodes. With 2 nodes, we will have like 5 partitions on every node. If we add a new node, those partitions are then redistributed across the cluster, but the total number of partitions doesn't change. It's still 10. It is never updated. It is never changed. So what it means is that now the mapping between the key and the node has to go through kind of 2 steps. We first map key to a partition, and then the partition is mapped to the node. And what's important here is that for the first step, we'll still use the same hashing function. The only difference is that instead of number of nodes that might change, we will use number of partitions, which will not change. This makes this mapping constant and consistent at all times. Hash code for a key never changes, partition count never changes. Therefore, this function is always consistent. The mapping between key and partition does not change regardless of, again, how many nodes we have, how many data we have. It doesn't even depend on whether we have this particular key in the database or not. This function will always give you the same result. The second step, of course, depends on number of nodes. For now, we'll again use like a very simple hashing. It depends on number of nodes, and therefore, we basically now rebalance partitions rather than keys, right? Therefore, when we do this rebalancing process, rebalancing check and rebalancing verification about which data should be moved and which data should be kept on the node where it belongs, we have to go through this fixed number of partitions rather than go through all the keys that we have. So when we get this notification from the database, from the discovery, the storage will only check these 10 partitions, as we have in this example, and will redistribute partitions rather than keys. So we kind of, during rebalancing, we essentially work with partitions as whole entities. We don't care about individual keys anymore. which makes the whole process much more efficient, because first of all, during this verification, we only have to check 10 partitions rather than millions or billions of keys. And also it's kind of easier to batch this data on the communication layer. All right, let's go back to the code. And let's see if this this code changes that we will do for rebalancing will fix this issue that we've had before. So switching to the next part. All right. So let's see what kind of changes we have here. So first of all, the storage. So as I said, we want to partition the data, right? So we'll do this first. And it's fairly straightforward. All we do here is this data map that used to be just a flat data structure with key value pairs. It now is kind of, it has two levels, right? Two layers. The top level map is the map of partitions, where the key is the integer, which is the number of partition, and the value is the actual map of key value pairs for that particular partition. Then in the put and get methods, we use the mapper.partition method. I'll show it in a second, which gives us partition for a key, and we get corresponding partition map from the top level map, and then update that internal map. And the same happens for the get method. And then we have the remap method, which basically just implements this whole logic of rebalancing that I've just described, earlier. It goes through all the partitions that we have and calculates the mapping for every partition. And then that's the important part. It checks whether the node this partition belongs to is the local node or not. It just compares the IDs. And if it is, then it basically keeps it in place or creates a new, creates a empty partition map for this particular partition, if it doesn't exist yet. If it does not belong to the local node, if it's not the same as the local ID here, then this means that we need to send this partition to another node it belongs to. So we remove this partition from our data structure and send it through the communication layer using this rebalance request, which is also introduced here. Rebalance requests, of course, includes the partition number and the actual data for that partition. And when it's received by one of the nodes, this onPartition received method is invoked, which basically just puts this partition map into our top level concurrent hash map data structure. So let's take a look at the mapper, because the mapper also changed. As I said, we have this partition map method here, which gets the partition number by the key, and the approach is the same. We just calculate the hash code, take the absolute value, and apply the modulo function based on the partitions number. The partitions, again, it's a constant number. It never changes. It's set to 10 here, and it will always be 10. We also have the node method that gives us a node for a partition, which, again, is very straightforward. It gets the topology from discovery and calculates the index based on the partition and the topology size. And the node method that we've had before, it is simplified. It just goes through this two-step process. It first calculates partition for the key and then node for partition. So basically that's the implementation. Yeah, the only thing that I missed is discovery notification. So when we discovery gets the notification about the topology change, it has to notify the storage. So for that, I've introduced this listener here, which is just a runnable, and it's provided into the join method when we basically join the cluster. And this listener is invoked anytime we receive some changes from etcd. So when this watch is invoked, we update the topology first, and then we notify this through this listener that this topology change occurred, and we updated our internal data structures in the discovery. And in the server, when we invoke the join, we actually provide the link to this remap method here. So whenever topology changes, this method will actually be executed through this mechanism, and the whole rebalancing will happen. All right, so let's try it out. So the test will be the test will be the same. I will start to server nodes first. I will run the client with both updates and reads. I will add one more node into the cluster, and we'll run the client with reads only. So now I expect that when I will add the new node, the rebalancing will happen, and therefore client will get all the correct results. So let's see what actually happens. All right, we have two nodes. Let's go to the client. Client doesn't have any changes whatsoever. Same application, same implementation. All right, so far so good. Everything is works as expected. So now let's stop the client, add one more node. All right. And let's run the client again with only read operations. So we don't update any data, we only read the data that is in the database. All right, and we got all the correct results. Regardless of the fact that some of the requests went to this new node, in particular requests for keys 0, 4, and 7, we got the correct results for all the keys, including those keys 0, 4, and 7 that are now stored on the server number 3. So this way we kind of achieve this data distribution not only when topology is stable, but also when topology changes. All right, so this basically kind of covers all the requirements that we have. There is one more thing that I wanted to go through, and I wanted to go through is just show you how the distribution actually happens, and it will reveal one other issue that is not, is not that obvious. So let's just take a look at the example of a data distribution, and we'll take a look at how 10 partitions will be distributed across 3 nodes for now. So again, we don't care about how keys are distributed across those partitions anymore. When we actually distribute the data, we work with partitions as kind of whole entities. So we don't really care about the keys anymore. So we have 10 partitions, and we need to distribute those 10 partitions across 3 nodes somehow. Our current mechanism is to detect node ID by applying modulo function to partition number, partition index, based on the number of nodes that we have, which is currently 3. So we have the list of partitions, which is from 0 to 9, in case we have 10 of them. And we'll get something like this for the node index, which is actually very straightforward. It's kind of a round robin thing because of the hashing function that we chose. So it's 0, 1, 2, 0, 1, 2, and so on. So if we visualize it and just show it on the picture, it will look like this. So some of the partitions will be on node 0, some of the partitions on node 1, some of the partitions on node 2, which is all good so far. Let's, however, take a look at what happens if we add one more node. So we add node number 4. So now we want to distribute 10 partitions across 4 nodes. The function is the same. The only difference is that the parameter is different, right? So now we apply the modulo function based on 4 nodes rather than 3 nodes. So we have the same list of partition numbers, and that would be the mapping. So first of all, of course, we have a couple of partitions that are now mapped to the new node, which is good. That's what we expect. And on the picture, it will look like this, right? Again, some of the partitions. Every node has some of those partitions in the among the total number of partitions that we have. So let's compare those two. So this is our new distribution with 4 nodes, right? This is our old distribution with 3 nodes. And there are 2 partitions, partition 3 and partition 7, which has moved from nodes 0 and 1 in this case to this new node that we've just added. So that's all good. That's what we actually want from rebalancing process. We want this new node to utilize the resources, to store the data and to process requests. So it's absolutely expected and absolutely what we want from this whole rebalancing process. However, if you look carefully, you'll see that there are a bunch of other data movements and a bunch of these red arrows, which actually becomes really messy. This is actually quite a big issue. So this is the data movement. These are data movements, and this is kind of a data reshuffling across the 3 nodes that we've had prior to the topology change. And this data movement, if you think about this, is completely redundant. It doesn't provide any value, right? Again, this the movement on partitions 3 and 7 does provide value. It allows us to use and utilize the resources of this new server that we've just added into the cluster. Other data movements are redundant. And it's actually even worse than that, because it's not only redundant, it uses a lot of resources, consumes a lot of resources. It consumes CPU, it consumes network. Even in this simple example with like 10 partitions and 3 nodes, we have more red arrows than we have green arrows. So this redundant data movement will require more resources than data movement that we actually want from the system. And that's a big issue, right? Because like in the best case, your rebalancing will take a lot of time. You will get a significant performance degradation during the rebalancing. In the worst case, it will just saturate your resources, saturate the CPU, or saturate the network, or both, and the cluster will fall apart, and you will have a downtime and all other things that you don't want to have. So we want somehow to avoid having this redundant data movements, and basically avoid having red arrows on this picture. So how we do that? Basically, we want to change the mapping. We want to change the hashing map mechanism that we currently use. And one of the ways of doing that is to use what is called rendezvous hashing. That is one of the algorithms that is basically designed to do exactly that. It's not the only one, but it's quite popular, and it's also very simple to explain. So I'm using this one as a reference. So let's see how it works. So we'll first assign certain IDs to the node. So every node must have a unique ID, which we already have actually in our code. In our code, it's UUID. In this example, I'm using just string IDs. It doesn't really matter. The only requirements is that the ID must be unique for every node, right? So we will then introduce a function, function h, which will be our hashing function. And the difference is that previously we calculated hash based on the key, or we just use the actual partition number. Now we'll calculate the hash based on the combination of a partition number and a node ID, right? So we'll utilize some hashing algorithm to calculate the hash based on these two values. And we'll also use the ABS. Again, we don't want to have negative values. So as a result, we'll get something like this, right? These are actually random values. It doesn't really matter. So for any partition that you want to get a mapping for, we will calculate the value for this function h for every node we have in the cluster. So we have 3 nodes. We'll get 3 values: h1, h2, and h3. And then we'll pick a maximum. So we'll find a maximum among those 3. In this particular case, that's h2, because it's bigger than h1 and h3. And this maximum value will basically just point us to the node where this partition will be stored, right? So if h2 is the maximum one, h2 is the value for the node 2. Therefore, this partition will be stored on the node 2. So that's how the algorithm works. And you can calculate this mapping for any partition whenever you need to calculate this mapping, right? How does it help with the situation that I've described before and with this whole data reshuffling thing that we want to avoid? So let's check what happens with if we add one more node. So where we add node 4, and therefore to calculate the mapping, we'll now calculate 4 values rather than 3, right? So we have h1, h2, h3, which do not change, of course, because hashing function will provide us consistent results based on the same values. Node IDs do not change. And as long as we calculate for the same partition, we'll get the same values for those 3. And we'll get some value for h4, which is the new one. So the h4, and there are basically 2 outcomes from there. The h4 can be either less than current hmax, or it can be larger than current hmax. I'm putting aside the hash collisions on purpose because, yeah, they of course can happen, but this is kind of typically handled outside of the algorithm, outside of the mapping, outside of the hashing algorithm. So we kind of here we assume that there are no collisions. So as long as there are no collisions, we have only 2 outcomes. It can be either less than hmax or it can be larger than hmax. In the first case, if h4 is less than hmax, we have the same hmax remaining, which is h2, right? So it doesn't change. Therefore, the mapping doesn't change and the partition stays on that node 2 where it used to be. In the second case, hmax is our h4 is our new hmax, right? Which means that the mapping changes and partition is moved to node 4. So in other words, we have only 2 possibilities here. It either stays where the partition either stays where it used to be, where it was, or it is moved to this new node that we've just added. So the algorithm by itself, kind of natively out of the box, provide this guarantee that a partition cannot be moved to any node that we used to have prior to the topology change. So again, it either moves to the new node or it doesn't move at all, which is exactly what we're looking for. And if we do the same exercise and create the same diagram, the same picture, we'll get this. So we have again like a certain distribution with 3 nodes, certain distribution with 4 nodes, and we have these 2 green arrows which depict the data movements that we're looking for during rebalancing, and there are no data movement other than that. So if we look at this, like the first node doesn't have any changes at all. It has all those 4 partitions remaining there, and other than 2 partitions moving to the node 4, node 2 and node 3 are also do not have any change. So this is called the minimal disruption requirement. by the way, if you ever read about this. And there are many ways, again, multiple ways of satisfying this requirement. And the rendezvous hashing is just one of the examples of the algorithms that helps us here. And this is, by the way, the one we use in Apache Ignite, for example. So it's quite a popular one. Consistent hashing is another one, which is also kind of probably the most popular one. You might have heard about this. So if you ever want to read about this, probably the consistent hashing is the next kind of option here. All right, let's see. And yeah, by the way, first of all, like we can actually take a look at this, and we can see that this actually happens, right? So this server number 3, that's my previous test, right? And as you remember, we had 2 nodes. Then we have written some data. Then we add node number 3. So this node number 3 now processes the requests for 0, 4, and 7, right? So here, if we take a look at this, so for example, right, keys 0 and 4 used to be on the first server before we added third node. And after the rebalancing, of course, we don't have this 0 and 4 keys 0 and 4 because they are on the new node now. But apart from that, we have a lot of other changes. So we have keys 1 and 5, which has arrived to this first node, evidently from the server number 2, right? So this is exactly what I'm talking about, right? So apart from this 3 keys that traveled from older nodes to the new node, we have other data movements here within the cluster. So let's take a look at the code one more time. So this change for the rendezvous affinity is actually probably the most straightforward one, because we actually only change this single method, the method that returns node by partition, which is, by the way, an important point, right? So this hashing function, kind of the whole other the system as a whole doesn't really know about how this mapping is achieved, right? It's all like this affinity this mapping function. We call it affinity function in Ignite, but basically it's the same thing. It takes care of the request routing, of the data distribution. It kind of always tells us consistently where the data is stored, and then all other components depend on that. So it's kind of it becomes very important part of the whole system. So that's the implementation of the rendezvous affinity. Again, the mapping from partition from the key to the partition doesn't change. It's still the same. We can use this basic hashing because it's constant. There are no issues there. But for the partition to node mapping, we use the rendezvous affinity, rendezvous hashing here. And we do this basically what I've described. So we calculate the hash based on the partition and the node ID. And we do that for every node in topology. So we have this internal loop here. And if the hash is the larger than the current maximum, then we pick, we update the maximum and memorize the node. And whatever was the node that corresponds to the maximum hash value, we just return it from here. And this way we achieve, we satisfy this minimal disruption requirement that we have. All right, so so with that, we basically covered all the requirements that we have. So we have, we created a database which can store data in memory, which provides basic key value API with put and get methods. And it provides us with all the basic scalability functionality. You can create a cluster with multiple nodes, they will act as a single database. The client is completely abstracted from the fact that there are multiple nodes. It only knows about the public methods. And data distribution and the request routing happen automatically within the system based on the mapping function that we have created. So with that, before going into questions, I wanted to mention that we're going to have the very first Ignite Summit, which is a virtual event, so anyone can join. And it will happen on May 25 this year. And it's going to be an exciting event. We're going to have a lot of interesting speakers. So you are certainly welcome to join. So with that, that's all I have. I'm ready to answer any questions that you guys have, and I will leave this Raffle slide for now as well. And at the end, we'll announce the winners. So any questions, guys?
Thank you very much. That was really interesting. I will wait a bit for questions, but I do have 3 questions myself, so I'm just going to wait a bit.
There's
yeah,
like there's a bunch of stuff in the chat.
Yeah. Okay. All right. So how do you handle nodes dropping? That's the first question from Robin.
Yes, that's a great question. In this particular implementation, I don't handle it. Again, for simplicity, of course, in the real database, you have to do that. I mean, first of all, the mapping itself doesn't change. So within the companies that I actually had there, except maybe for discovery, doesn't really, the node failure is the same as the node addition, right? So when we remove a node, the mapping changes. Therefore, the mapping function gives us different results. So we can still modify the storage, do the rebalancing and all that. So that's the first thing. The second thing that, of course, in a real distributed database, you will always have a certain level of replication, right? Like in Ignite, we call it backup copies, for example, right? So if whenever for any data set that you have, for any cache or for any table, you can have at least one backup copy for every entry, for every partition rather, that you have. In which case, the mapping function, instead of giving you just a single node for a partition, it will be designed to give you 2 nodes or 3 nodes or 4 nodes for every partition, and it will be distributed this way. Therefore, when you lose a node, you still have the data, right? So this way you kind of avoid losing the data in the first place. And of course, on the discovery level, discovery typically is much more complicated process. So except of this, apart from this meta storage that I've implemented here, it usually will also have kind of a membership protocol of some sort with heartbeats going back and forth, detecting that nodes are there, and if nodes is not available, is not responsive, it will be removed from topology and all these kind of things. So I also don't have it here. So there are kind of I guess 2 parts here. First of all, the detection of the failing node, which happens on discovery level based on certain membership algorithm, and on the storage level, you will typically have backups or replicas to make sure you don't lose the data. But the rebalancing process and the mapping itself doesn't really change. It all works in the same way.
Yeah. Okay, we have a question from Martin. Is rebalancing synchronous or asynchronous?
Usually it is asynchronous. Again, in this implementation, it's kind of simplified. So I'm assuming that it will be completed before I run any operations.
Yep.
In real databases, it is typically asynchronous because it can consume quite a bit of time, and it will happen in background and will not interfere with the whole application workload. The way it's achieved, it's very, I don't want to go into too deep details, but basically there are many different mechanisms of achieving that. You like Ignite, for example, it basically maintains, in a nutshell, it maintains copies of when it moves a partition, instead of just removing it and sending it to a new node, it kind of maintains both of them in the meantime during the process, and the request can go to either of them, right? And if there is if a request goes to the new partition, to the new version of partition, and it hasn't received some of the data yet, it will kind of request it from the old one. So there are just certain kind of local optimizations there and local mechanisms that are applied in order to cover all those different race conditions that are possible. But generally speaking, of course, any mature system will make sure that this happens in background in asynchronous fashion, so that you don't have to stop the application for half an hour until the rebalancing completes. Because rebalancing can, of course, it will take quite a bit of time if you have terabytes or petabytes of data or whatnot.
Yeah. Another question from VV. How would you decide the number of partitions?
So generally speaking, there is the only rule that is there is sorry, number of partitions should be significantly larger than number of nodes. Like what we do in Ignite is we put it to 1024 by default, which seems to be very reasonable number based on my experience. So yeah, we do have some of the users that have hundreds of nodes, like 500, 600 nodes or something like that, and they would increase this number. It is configurable. It just, you have to do this in advance. You cannot change it in the runtime. So once you created your database, you cannot change it, but you can configure it before you create it. So yeah, they would increase this number to whatever they need. But for vast majority of use cases, the default that we have, it actually works. So there is no strict rule on how to choose that, but you definitely need more partitions than you have nodes. Because if you think about this, if you have 10 nodes and 5 partitions, you will not be able to use more than 5 nodes, just theoretically, right? So you need more nodes and more partitions than you have nodes, and also due to kind of this probabilistic nature of the distribution, because we're using hashing here, you need kind of significantly more partitions than nodes to make sure that the distribution is even. So the more partitions you have, the more even the distribution would be based on this probabilistic distribution.
Yeah. Adam has a question. I can ask it, Adam, or if you want to unmute yourself and ask it. Happy.
It's okay. I think it's already been covered, but thank you very much. And thank you for a great talk.
Great. Another question is from Timov. I'm sorry, Timov. I'm not going to be able to pronounce your last name here. But what does the rebalancing look like from the client's perspective? Is the client blocked while it's happening?
Yeah, that's basically the same thing, right? Yeah, it happens in background. It does not block the client, and yeah, so the application continues to work. You can expect certain performance degradation, of course, because network is consumed and all that. And there is a trade-off between, essentially the trade-off between how much degradation you will get versus the time of the rebalancing. And it's up to you, like, typically it will be configurable as well to a certain extent. But I don't know, I'm not aware of any distributed database that would block everything completely during rebalancing.
Great. One more question about the GitHub link for the code.
Yeah, it will be provided. So it's on GitHub, and I guess we'll send it afterwards somewhere.
Okay, we will try to put it in the YouTube link on the recording,
yeah,
guys.
Exactly. Yeah.
Provided. Great. Any other questions? I have still a few questions that were not asked, so maybe I'll ask them if that's okay with you. Here you're distributing data but you're not really synchronizing data. I think you covered this in the backup point before, but if you want to synchronize certain amount of data between all the nodes, just to ensure that when something drops, you still have the data somewhere, would you still kind of use the same hashing mechanism, or would you kind of re-architecture this a bit differently?
The hashing mechanism would be basically the same. So like if you use, as I said, yeah, you will have backup copies, replicas, like, and basically will be like with rendezvous hashing, for example, like where in this implementation, I was picking just the first one, right? If you want to have a backup, you will pick the first two, and that's it. And it will serve all the same purpose. It will also like avoid the data reshuffle or whatnot, and will minimize the data movement during rebalancing. It will give you 2, 3, or 4 nodes instead of 1.
Yeah. One more question. I'm sorry for troubling you.
No problem.
And by the way, the GitHub link was posted by Simia, so it is available in the chat. And again, it will hopefully be posted also in the YouTube channel as well. You kind of depend on, in the discovery phase, you depend on etcd or Zookeeper. What happens, what would you do in order to kind of mitigate if etcd is down, for instance? Or yeah.
So yeah, etcd itself is basically, it's kind of replicated database based on Raft protocol and whatnot. It's very limited amount of data that you can store there and so on, but it's, you know, more than enough for this kind of meta purposes. So, you know, if you depend on an external system, it will typically provide this kind of functionality. Internally, again, like Ignite does that based on some proprietary protocol. It can basically kind of creates a ring of nodes and distributes this information across this ring and this kind of thing. So it's there are different ways of doing this, right? So yeah, if you depend on the internal system, then this external system should provide this durability and availability. If it goes down, it goes down. There's nothing you can do with that. If it's an internal mechanism, then it's up to this mechanism to make sure that it also works. Yeah. And there are many ways of doing this, like many options that you have there.
Yep. I want to remind everyone to not leave because the Raffle results are going to come in a few minutes. And yeah, I think that's it about the questions. Any other questions, guys?
Hi, this is Fahad. Thanks very much for a very good session, Valentin. That was really nice. I was just wondering if you have got any recommendations for like background material on this, like, you know, any good resources you came across while you were, you know, you've been working on Apache Ignite for a while. So like you found out about the Rendezvous algorithm. You know, is there any recommended reading you might suggest to get started, you know, if you want to kind of learn this in more detail?
Well, if you don't win this first book from Martin Kleppmann, then I would recommend to buy it. That's a very great resource. It kind of covers all the it basically goes through all the different technologies and concepts, I would say, in distributed systems. So it's a very good read. Might be a good starting point. And generally, you know, I would just learn how databases work. You know, we luckily live in the world of open source. So feel free to join Apache Ignite community, learn about Apache Ignite, for example. We have a very active community that always ready to help. That might be one of the best ways to learn, actually.
Excellent. Thank you very much.
Sure.
Great. I guess I'll leave you to announce the Raffle winner.
Yeah, let me do a raffle. So our magical button. And our first winner is Saurav Roy. I hope that I pronounced your name correctly.
Thank you very much. Yeah, it was correct.
Great. I'll contact you by email you put into this survey.
Yeah, sure.
Congratulations.
Thank you very much.
My congratulations. Think about the book you would prefer. All 3 books, by the way, these are from our survey inside GridGain and Apache Ignite community. So that's like the top of Apache Ignite developers.
Excellent.
And our next winner is Mekuria Tegange. I'm sorry if I made it wrong.
Yes, you're right. Thank you.
Cool. I'll contact you with the email. I think we'll need to check the delivery options. And our last winner is Adrian Woodhead. Adrian, my congratulations.
Brilliant. Thank you very much.
I'll contact you today using this email.
Awesome. Thank you.
Thank you all. I hope that you like your books. And if you didn't win, just check them out. They're really good if you like to know more about distributed data systems. And join Apache Ignite community. Ask questions, try code, try samples, and I hope that you'll enjoy that. Thank you very much.
Great. Thank you very much, guys, and congratulations to the winner. I just want to remind you again that this recording is going to be available on YouTube soon. And thank you very much for Valentin for his amazing session. Thank you very much, guys.
Sure. You're welcome, guys. Thank you. Thank you for listening.
Thank you very much.
Thank you. Bye.
Thank you.
Yes.
Thank you so much.
Thank you very much.
Have a nice evening.
Bye.